I'm from Carnegie Mellon University. Today, I want to introduce my solution for KDD-CUP 99 problem. First, I will introduce the problem of KDD-CUP 99, and then I will give a brief introduction of the datasets of KDD-CUP 99. Then, I solve this problem from two aspects. The first aspect is feature engineering, and then I do model selections. Finally, I summarize all the work I have done and give the brief introduction of the future work I'm going to do. First, network security is becoming increasingly important with enormous growth of computer networks usage. KDD-CUP 99 problem is aimed at to build a network intrusion detector which is capable of distinguishing between bad connections and good normal connections. The dataset contains a standard set of data including a wide variety of intrusions simulated in the military network environment. The connection can be divided into abnormal connection and normal connection. Abnormal connection includes the DOS connection, R2L connection, U2R connection, and the probing connections. The corresponding labels is as follows. And the dataset includes 41 features. It includes basic features of individual TCP connections, content features within a connection suggested by domain knowledge, and the traffic features computed using 2-second time window. However, there are two issues affecting the performance of evaluated system. The first issue is that is a high number of redundant records in the datasets, and the second issue is the difficulty of comparison of ideas of the datasets. NSL KDD datasets is used which have solved these problems, so I use an NSL KDD to solve this problem. Next, I do the feature engineering work. It includes two aspects. The first is normalization, and the second is reduced dimensionality. For normalization, I use the two methods. The first method is by subtracting average and then dividing by standard deviation. The second method is subtracting minima and dividing by range. And then I reducing the dimensionality using principal component analysis method. Principal component analysis performs a principal component analysis on the given data matrix and returns the results as object of class. We can see from this picture is that it shows the relationship between the principal components and the variance. Principal components 1 to principal components 8 covers most of variations. So I use the following selected features to do my experiments. This is the code I used to do feature engineering. And this is a rotation of principal components analysis. For the model selection, I first define the performance matrix. I use the kappa value. Kappa value measures inter-rater agreement for categorical items. And I also use confusion matrix. It is a specific table layout that allows visualization of the performance of algorithms. And then I use the neural network model k-nearest neighbor model, support vector machine model, and the decision tree model. For the neural network model, it emulates how the human brain works by having a network of neurons that are interconnected and sending simulating signals to each other. This picture shows how the neural network works. This is the code I write to the experiments. And then I use k-nearest neighbors. It is also called instance-based learning. Next, I use k-nearest neighbor. It is also called instance-based learning. The training process is basically memorizing all the training data. To predict a new data point, we find the closest k-neighbors from the training set and let them vote for the final prediction. For the distance function, I use Euclidean distance, and the voting is weighted among the k-nearest neighbors based on their distance from the new data point. This picture shows how the k-nearest neighbor works, and this is the code I used to do the experiments. For the spot vector machine model, it provides a binary classification mechanism based on finding a dividing hyperplane based between a set of samples which nearly separable. If the data distribution is fundamentally nonlinear, the trick is to transform the data to a higher dimension, and hopefully the data is linearly separable in that higher dimension. This picture shows how the support vector machine works. This is the code I use to do the experiments. Finally, I use the decision tree. It learns a decision tree and uses that to predict the output Y for future scene data. This picture shows how I used a decision tree. This is a code I write to do experiments. And finally, I summarize all the work I have done by this chart. From this chart, we can see that the accuracy of feature engineering is higher than the accuracy without feature engineering. And also, the accuracy of neural network and decision tree is higher than spot vector machine and the KN model. So finally, we can summarize that the best features combination is as follows, and also the best model is neural network and decision tree. So by combining best features and best model, the accuracy increases to 85%. So in the future, I will do more work about the efficiency. Although neural network performance is well, it is slow. However, detection requires a quick response, so we need to explore more efficient algorithms. So this is a presentation about KDD-CUP 99 problem. If there is any problems, feel free to contact me. Thank you.